Hi everyone. In this video, we're going to go over physical properties of alkanes as well as some reactions of alkanes. So alkanes are non-polar molecules. So that means they're not going to have any dipole-dipole interactions or hydrogen bonding, right? So non-polar molecules like alkanes will have weak intermolecular forces. So can you remember what that really weak intermolecular force is called? So there are actually two names for it, either London dispersion or van der Waals. So we'll just call these van der Waals forces, but you could also call them London dispersion forces. All right, alkanes also are hydrophobic, which means that they do not dissolve in water. Another way to say that is they're not soluble in water. So off to the right, you can see we have oil and water, and the oil is separate from the water, similar to alkanes. Also, alkanes have low density, so if you have water and some sort of alkane, they're going to form two layers, similar to the oil and water on the right. And the alkanes, because they're less dense, will float on top of the water. So remember, density is equal to mass over volume. Now, the density of water is about 1 gram per milliliter. So alkanes will have densities that are less than 1 gram per milliliter. Also, alkanes have melting points and boiling points that increase with molecular size, and we'll see a chart of that in a bit. All right, so down below you can see a table with the first 10 simple alkanes, and there's actually a term for these alkanes. We call them a homologous series. So a homologous series is a group of compounds with the same functional class. So in this case, that would be alkanes. And they only differ by a CH2 group. All right, so we're going from 1 carbon all the way up to 10. And notice that as we add more carbons and hydrogens, the boiling points and melting points are going from negative numbers either to positive numbers or closer to 0. So they're increasing. So again, melting points and boiling points increase with size. So this makes sense if we imagine, for instance, let's see, let me go back so I have some room. So let's imagine methane, CH4, and let's say it's next to another methane molecule. Now, really, the molecule is going to have electron density all the way around. So there's really only this kind of small sort of contact point, but not really since there's electrons there. And remember, the force between these two molecules is really weak. Now, what if we have a larger molecule, something with a lot of carbons? And then imagine there's hydrogens all the way around this molecule. And then let's say we have another copy of that same molecule nearby. So this is a much bigger molecule, and there's more potential for these contact points or van der Waals forces between the two. So the more van der Waals forces you have between two molecules, the more energy that you need to break them apart from each other. So for instance, if you're boiling something, you're trying to take liquid molecules and turn them into gases. And gases are going to spread apart to fill up the space in the room, right? So in order to take a liquid to a gas, we have to break all of those forces between the molecules. So if you have something really small like methane, it won't take very much energy to break those two methane molecules apart or break up their van der Waals forces. But if you have something like pentane with 5 carbons, there's more potential for more interactions between those two, so it's going to take more energy or more heat to break them apart. Okay, and then we can also see this in the graph shown here. So on the y-axis, we have boiling point, which is increasing, going up. And on the x-axis, we have the number of carbon atoms, which is increasing, going to the right. So methane with 1 carbon atom is down at the bottom here, and it's a gas, and its boiling point is really, really low because, again, 2 methane molecules won't have very much attraction to each other, so it's going to be really easy to break those apart, right? However, when we start to get up to, for instance, let's say 8 carbons, now the boiling point is much higher. It's around the boiling point of water because, again, it's going to take more energy or more heat to break apart the intermolecular forces between these really long chains of carbon atoms. Okay, and again, you can see this is a really nice curve here. So as you add more carbons and hydrogens onto your alkanes, the boiling point is going to increase. Additionally, the melting point will increase too. Okay, so let's talk about some reactions that we can perform with alkanes. Unfortunately, there aren't very many reactions we can do with alkanes. So alkanes and cycloalkanes have really low chemical reactivity because of their covalent bonds. Remember, there's carbon-carbon bonds and carbon-hydrogen bonds, and covalent bonds are really strong compared with bonds in other organic families. So really, the only 2 reactions that alkanes and cycloalkanes can perform is combustion, which you might also know as rapid oxidation, or halogenation under heat and or light. Okay, so you might remember combustion reactions from Chemistry 121, and we'll talk about those in a bit, but I wanted to go over halogenation because this might be a little newer to you. So with halogenation, let's say we have methane again. It's kind of the easiest example. What we're going to do is add a halogen to it. Or rather, we're going to replace one of the hydrogen atoms with a halogen. So what we're going to do is use something like bromine or chlorine, for instance. Let's just use chlorine. So that's a halogen. Remember, the halogens are fluorine, bromine, chlorine, iodine. I might have put them out of order there, but essentially what happens is we're going to add heat and light and replace one of our hydrogens on methane with a chlorine atom. And then our other product will be hydrochloric acid. All right. So this is a really handy reaction. It really only works for bromine and chlorine. Fluorine is really reactive. So fluorine wants to react with everything, and it reacts really violently, so we don't really use that one. Iodine reacts too slowly because it's such a big atom or molecule if you have I2. So we really only use bromine and chlorine for halogenation. Now, many alkanes are used as fuels. So methane, for instance, is a common natural gas. It's probably what you have if you have natural gas that goes into your home. Propane is used in gas grills. Butane is used in lighters. And then gasoline is actually a mixture of different hydrocarbons. So it's not necessarily just one alkane, it's kind of a mixture of them. But that brings us to combustion. So you might remember that if you react, for instance, methane with oxygen, you're going to end up forming carbon dioxide and water. You're also going to produce some energy in the form of heat. And this is why methane is often used for natural gas on a stove, for instance, or in a fireplace, because you get a lot of heat out of that reaction. Now, typically we assume that we have an excess of oxygen available for these reactions. But if maybe you don't have enough oxygen available, then the reaction changes slightly. And you might actually end up producing carbon as one of your products. But don't worry too much about incomplete combustion. We'll just talk about complete combustion here. Now also with complete combustion, notice that we have molar ratios between all of the different molecules. So we have one methane molecule that reacts with two oxygen molecules, and then we produce one carbon dioxide molecule and two water molecules. Oh, whoops. So just keep in mind that those ratios do exist because you might have to balance equations in reactions in the future. So for instance, instead of methane, what if we had ethane, C2H6, and that reacted with oxygen to produce carbon dioxide and water? Well, we need to make sure by the law of conservation of mass that we have the right number of atoms on both sides of the equation. So if we kind of go through this, I'm going to start by balancing carbon. So how many carbons do we have on the left-hand side of the equation? 2. And how many do we have on the right-hand side? Only 1. So I'm just going to make a little table here of reactants versus products. And I'm just going to write that we have 2 carbons on the left, but only 1 on the right. Okay, so then what about hydrogens? How many hydrogens do we have on the reactant side versus the product side? So we have 6 hydrogens in the reactants, but only 2 in the products. All right, now what about oxygen? How many do we have in the reactants versus the products? So we have 2 oxygens in the reactants. In the products, we have 2 plus 1. So that's a total of 3. So what I recommend here is to start by balancing carbons and hydrogens, and we'll leave the oxygens for last since oxygen is split between 2 products here. So let's start with carbon. That's easy. We're just going to put a 2 in front of CO2. So that changes the amount of carbon in the products to 2. And it also changes the number of oxygens, right? Because we're going to multiply 2 by 2 to figure out the number of oxygens. So we have 4 oxygens from CO2 and only 1 from H2O, so that changes this to 5 oxygens. So again, oxygen's a little weird right now. We'll come back to that later. So now let's balance our hydrogens. We have 6 hydrogens on the left, 2 on the right. So I'm going to put a 3 in front of H2O because that will give us a total of 6 hydrogens on both sides. Now again, that's also changing the number of oxygens. So now we have 4 from CO2 and 3 from H2O, so that's 7. Now, if you come across this weird amount where you have an odd number of oxygens in the products, here's a little trick. Just multiply everything by 2. And that will solve all of your problems. Okay, so we're just going to multiply all of that by 2. So let me just rewrite all of those coefficients. So we'll just multiply all of that by 2. All right, so we'll have 2 C2H6. 2 O2, 4 CO2, and then 6 H2O. Okay, so now let's go down and kind of rebalance everything down here. All right, so we have, let's see, 2 times 2 carbons, which is 4 in the reactants. And then we have 4 carbons in the products. Check. All right, let's see, for hydrogen, we have 2 times 6 hydrogens, so that's 12. In the products, we have 6 times 2, so that's also 12. Great. So now for oxygen, we have 2 times 2, which is 4 oxygens on the left. And then on the right, we have a bunch. We have 4 times 2, which is 8, plus 6 times 1, so that's 6, so that's 14. Oh man, okay, so what can we do here? Well, we basically need to multiply this O2 by something to make sure we have a total of 14. So what do we multiply this 2 by to get 14? 7, right? So we're going to change that coefficient to 7, and that will give us 14 oxygens on the left. Okay, so again, balancing can get kind of tricky with these combustion reactions. So just be careful with those. But if you do want extra practice with balancing equations, just let me know. I can always put up a worksheet for that. And I think that's it for our chapter on alkanes. So in the next chapter, we're going to talk about alkenes and aromatics, so the unsaturated hydrocarbons. So I will see you then.